The prevailing theory among most scientists is that the current explanations regarding the universe's origins continue to be the most prominent interpretation of its early evolution. This theory connects the formation of stars and planets, which ultimately gave rise to life, including humans. Despite its peculiar name, the Big Bang theory offers a thorough understanding of what could have transpired at the universe's inception. In the beginning, the universe was contained within an incredibly minuscule 29 seconds space, much smaller than the head of a pin, and was densely packed with particles. From this highly compressed state, a massive explosion of energy and matter occurred, known as the Big Bang. This cataclysmic event, which took place billions of years ago, triggered the expansive history of the universe. However, as scientific knowledge progresses, inconsistencies have surfaced, challenging the assumptions underlying this theory. When NASA launched the James Webb Space Telescope, JWST, the largest and most advanced space observatory ever, 1 minute and 4 seconds, constructed, experts anticipated that its data would confirm the Big Bang theory. Yet, within just 1 year of operation, the telescope astonished scientists with its exceptional capacity to peer back into the universe's ancient past. The groundbreaking abilities of the JWST have uncovered galaxies so old that they challenge our current understanding of the universe's origins. This revelation has sparked a lively debate regarding the potential existence of matter from before the Big Bang. A significant 1 minute and 35 seconds milestone came when cosmologist Rohan Natu, analyzing data from the JWST, identified a galaxy that emerged shortly after the Big Bang, marking it as the most distant galaxy observed to date. This discovery sent shockwaves through the scientific community, emphasizing the extraordinary potential of the James Webb Space Telescope. The scope of the JWST's ability to reshape our understanding of the cosmos is just beginning to unfold, bringing new insights into the earliest stages of the universe. This period, which 2 minutes and 6 seconds, loosely connects to prior cosmic events, holds the key to unraveling the formation of the first stars and galaxies. The JWST findings have contradicted existing theories, unveiling galaxies with features that defy earlier expectations. The sudden influx of early galaxies has ignited intense scientific inquiry, compelling researchers to reconcile these new findings with established models. As scientists continue to explore these results, they are confronted with fundamental questions about the universe's very nature and the forces 2 minutes and 40 seconds that shaped its evolution. In addition to its impressive scientific contributions, the JWST's strategic location, 1.5 million kilometers away from Earth, shielded from interference and kept near absolute zero by its sunshield the size of a tennis court, provides a distinct advantage. This positioning enables the telescope to make uninterrupted observations of the universe, free from the distortions of Earth's atmosphere. Equipped with a massive primary mirror and advanced instruments, the JWST was specifically designed to capture details 3 minutes and 14 seconds about the early universe that were previously out of reach. This early cosmic era, known as the Great Dawn, began around 200 to 300 million years after the Big Bang, marking the formation of the first stars and galaxies. The processes behind this formation remain a central focus of research, with theories exploring the roles of dark matter, dark energy, and the interactions between gas and dust in star creation. The JWST's ability to observe galaxies from this pivotal period offers cosmologists a rare opportunity to test their existing 3 minutes and 46 seconds models of the universe. By studying these ancient galaxies, scientists can validate current theories or uncover gaps in understanding that may lead to groundbreaking revelations. Initially, it was expected that the JWST would only detect a few faint, small galaxies. However, its findings vastly exceeded these expectations. The first images of the distant universe captured by the telescope revealed an astonishing number of galaxies of various sizes, ages, and luminosities, far beyond what was predicted. This unexpected surge of early 4 minutes and 21 seconds galaxies has triggered a race among astronomers to rewrite the records of the earliest massive systems. New discoveries are continually emerging, leaving even the most experienced scientists in awe. After the JWST discoveries, both experts and the public have been eager to examine the advanced features of these early galaxies. Some researchers have speculated that potential errors in how the telescope interprets large-scale observations might account for some of these surprising results. However, the prevailing consensus is that these 4 minutes and 53 seconds. Findings represent a paradigm shift in our understanding of the early universe, offering an exciting glimpse into how much more we could learn. The recent revelations about early galaxies have raised profound questions about the nature of the universe, challenging traditional cosmological models. While some researchers are working to incorporate these discoveries into existing frameworks, others suggest that they may signal the emergence of a more intricate and mysterious universe than previously imagined. A crucial question. 5 minutes and 23 seconds. That remains is how the universe we know today emerged from the chaotic conditions of its early stages. The JWST's early discoveries could radically change our understanding of the Big Bang and provide new insights not only into distant galaxies and ancient cosmic structures but also into the makeup of our own Milky Way galaxy. As Mark McFadden, senior scientist for science and exploration at the European Space Agency, aptly stated, "You build these machines not to confirm theories but to break them. You simply have no clue how it will." 5 minutes and 54 seconds. Break. The history of the JWST traces back to 1985 when the Space Telescope Science Institute, STSCI, began laying the foundation for a successor to the Hubble Space Telescope. At that time, G. Weir, then the head of STSCI, was tasked with envisioning what would follow Hubble. Despite initial skepticism, Weir and a small team began planning for what would eventually become the James Webb Space Telescope. Unlike Hubble, which primarily observes visible light, the JWST was designed to observe the universe in the infrared. 6 minutes and 28 seconds. Spectrum, enabling it to peer deep into space. This infrared capability is crucial for studying distant galaxies, whose light has been stretched into the infrared range due to the universe's expansion, making them invisible to telescopes like Hubble. With its large, cold, star-like mirror, the JWST has become an invaluable tool for unlocking the mysteries of the early universe. The need for such a telescope became evident in 1995 when the Hubble Deep Field observation revealed a large number of galaxies in a region of the sky. 7 minutes. Previously thought to be empty. This discovery demonstrated the richness of the early universe and underscored the need for a more powerful telescope capable of probing deeper into space. After years of development and an investment of approximately $10 billion, the JWST was launched on December 25, 2021. By July 2022, it was ready to embark on its critical year of scientific observations. Programs like the Early Release Science, ERS, and the General Observing Program were designed to search for early galaxies. While initial 7 minutes and 34 seconds expectations were modest, the results far exceeded. Which can take months, researchers opted to share their findings on preprint servers like AR-14, allowing for immediate public access before undergoing formal peer review. This approach facilitated rapid feedback and 8 minutes and 39 seconds. Discussions through online platforms such as Twitter, where established scientists engaged in real-time conversations about the findings. Rohan Natu referred to this novel process as science by press release, and the ensuing surge of conversation was both intense and unprecedented. As the debates raged on, new observations from the James Webb Space Telescope continued to flood in, each more surprising than the last. Researchers quickly realized that some of the galaxies detected by the JWST were not only older than expected but also more massive than conventional models predicted. One such discovery was a galaxy labeled GN-Z11, initially thought to be one of the oldest known. However, fresh data suggested even older and more developed galaxies, indicating that star formation may have begun earlier than previously believed. This revelation sent shockwaves through the cosmology community, as it challenged the very foundation of the Big Bang timeline. 9 minutes and 45 seconds. The unexpected abundance of ancient galaxies posed a significant dilemma. How could these massive structures have formed so soon after the universe's inception? Some astrophysicists speculated that our understanding of cosmic inflation, the rapid expansion of the universe after the Big Bang, might need revision. Others proposed that undiscovered processes in the early universe could have accelerated star and galaxy formation far beyond current estimates. One radical idea gaining traction suggested that what we perceive as the beginning of the universe might not be the true starting point. Instead, the Big Bang could have been just one phase in a much larger, cyclical cosmic history. This controversial hypothesis, known as the Big Bounce theory, posited that the universe may have undergone multiple cycles of expansion and contraction, each culminating in a rebirth of cosmic structures. 10 minutes and 23 seconds. Meanwhile, JWST's advanced spectrometers provided detailed chemical analyses of these early galaxies. To the astonishment of astronomers, some galaxies exhibited heavy elements like carbon, oxygen, and even iron, elements that should have taken billions of years to form through stellar fusion and supernova explosions. This anomaly suggested that early stars were more massive and short-lived than expected, rapidly enriching their surroundings with complex elements. If these findings held, they could redefine the entire timeline of cosmic evolution, forcing scientists to reconsider how quickly the universe transitioned from a primordial state to the intricate structures we see today. 10 minutes and 58 seconds. Beyond distant galaxies, the JWST also turned its infrared gaze toward exoplanets, searching for potential signs of life. One particularly intriguing target was TRAPPIST-1e, an Earth-sized planet located within its star's habitable zone. Using its powerful instruments, JWST detected atmospheric signatures that hinted at the presence of water vapor and possibly even organic molecules. If confirmed, such findings would mark one of the greatest scientific breakthroughs of all time, the first real evidence that life-sustaining conditions exist beyond Earth. The implications of this discovery reached far beyond astronomy, raising profound philosophical and existential questions about humanity's place in the cosmos. 11 minutes and 35 seconds. As the second year of JWST's mission approached, excitement within the scientific community showed no signs of slowing. New research initiatives aimed to refine models of dark matter and dark energy, two of the most mysterious components of the universe. Meanwhile, efforts were underway to develop next-generation telescopes that could work alongside JWST, extending its capabilities even further. Some proposed projects, such as the Habitable Worlds Observatory, aimed to directly image exoplanets and analyze their atmospheres for biosignatures. Others, like the proposed Cosmic Dawn Telescope, sought to investigate the very first moments of the universe with even greater precision. 12 minutes and 10 seconds. Despite the countless mysteries that remained, one thing was clear. The James Webb Space Telescope had already reshaped our understanding of the universe in ways few had anticipated. With every new discovery, it pushed the boundaries of human knowledge, challenging old assumptions and opening doors to new possibilities. For cosmologists, astrophysicists, and space enthusiasts alike, the journey had only just begun. As the James Webb Space Telescope, JWST, continued its mission, astronomers found themselves at the forefront of a cosmic revolution. Every new dataset challenged previous assumptions, forcing theorists to refine their models or, in some cases, abandon them altogether. One of the most unexpected discoveries came when JWST detected an enormous, ancient black hole, one that should not have existed so early in the universe's history. This black hole, lurking within a galaxy just a few 100 million years after the Big Bang, was far more massive than theories predicted. According to conventional astrophysics, such a behemoth should have taken billions of years to form. Yet, there it was, a cosmic enigma defying explanation. 13 minutes and 21 seconds. Scientists scrambled to make sense of this anomaly. Some suggested that black holes in the early universe could have formed through direct collapse, bypassing the gradual accretion process typical of later epochs. Others speculated that unknown physics, perhaps involving exotic particles or hidden dimensions, might be responsible. Adding to the mystery, JWST's spectroscopic data hinted at an unusually smooth distribution of dark matter around these ancient galaxies. This was at odds with previous simulations, which suggested that dark matter should have formed dense, clumpy structures. If confirmed, these findings could point to new, undiscovered properties of dark matter, an entity that, despite constituting most of the universe's mass, remains one of its greatest mysteries.